Good morning, students. Today we will take up the first chapter and the first topic of the fifth semester chemistry syllabus, that is carbonyl compounds, which is about aldehydes and ketones. So let's start with the topic. Carbonyl compounds are what? Either aldehydes or ketones. Aldehydes means general formula RCHO and ketones RCO R dash. So if we see the general formula, it is CnH2O, H2NO. So in ketones, when both the groups are same, they are called as simple ketones, and when they are not same, they are called as mixed ketones. Now, if you see the nomenclature, one containing the single carbon atom, it is called as methanol. Then containing two carbon atoms, called as ethanol. Then containing three carbon atoms, it's called as propanol, and similarly. Now, if you see the structure of the carbonyl compound, we see that the bond between carbon and oxygen is a double bond. That means one sigma and one pi bond. And since that is why, because the bond is double bond, so it is an sp2 hybridization. That means three sp2 hybrid orbitals form three bonds, one with oxygen and two with the other groups attached to it. Now, if we see the angle between them, it is 120 degrees. Now, another important observation is that there is difference in the electronegativity between carbon and oxygen. Why? Because oxygen is more electronegative. That is why what happens is that in such compound, if you see there is a partial positive character on the carbon atom and partial negative character on the oxygen atom. Here in the diagram below, it should be oxygen with delta minus, not carbon. Now, since the carbonyl group is planar, so there is a possibility that the attacking species will attach itself to the carbonyl group from either above or below the plane. That is why it is a reactive group. That is why carbonyl groups जो carbonyl compounds होते हैं उसमें जो carbonyl functional group होता है वो reactive होता है. क्यों? Because of this polarity, difference in the polarity of carbon and oxygen in the CO bond. The same thing is written in the second point. The polar nature of the carbonyl group enhances the rate of reaction. Positive charge on carbon invites negatively charged groups and vice versa for the oxygen atom. Now, if you see the carbonyl structure, the ketone CO bond has length 1.23 angstrom, and the energy to break this bond is around 178 kilocalories per mole. And if you see that, compare it to the alkene C double bond C, the length is 1.34 angstrom. So in this, the length is smaller, and the bond energy is 146 kilocalories per mole. Now, the carbon is sp2 hybridized, and the CO bond is shorter, stronger, and more polar than the CC bond as compared to that in alkenes. Now, if we see the synthesis of aldehydes and ketones, so there are four methods of preparation. First, from acid chlorides, it can be prepared. Then from 1,3-dithiones, it can be prepared. Then from cyanides or nitriles, and then from carboxylic acid. So let us take up each of them one by one. So from acid chlorides, the most common preparation is the Rosenband reduction. That is the reduction of RCOCl or the acid chloride with hydrogen on a palladium barium sulfate catalyst. And the product is an aldehyde. Like if we take acetyl chloride and then we reduce it over this catalyst, the product will be acetaldehyde with the removal of a HCl molecule. Similarly, the benzoyl chloride, the benzene derivative, will give a similar benzaldehyde. Now, if we see the mechanism, what will happen is that the H2 will divide as, H plus and H minus, and then one of the H minus will attach itself to the oxygen atom, and then simultaneous removal of the chloride ion, and then shifting of this, OH bond, and then subsequent removal of the H plus group. So there are other ways also to do this, to convert acid chlorides to acetaldehyde. So we can use different other reagents also. So we can use lithium aluminium alkyl catalyst, and then we can also do the same with Grignard's reagent, that is RMGX or CH3MgBr, like in this case, which is a nucleophilic addition. Then the second one is 1,3-dithiones. So dithiones means having two sulfur atoms at the first and the third positions. Now, when it reacts with butyl lithium, and butyl lithium, which is the catalyst here, so what will happen is that it will result in the alkane form of the butyl lithium. I mean, it will form butane. So from butyl lithium, it will form butane, and the subsequent reduction to from dithiene to 1,3-dithiene to dithiene anion. Now this, what happens is that this 1,3-dithiene, this can be deprotonated. So out of the 2 hydrogen atoms, one can be removed. And how can this be removed? In presence of a strong base, which is n-butyl lithium. So it will result in a carbonyl, that is a group, alkyl group with minus charge, which is then stabilized by the electron withdrawing effect of the sulfur atoms. Then what happens is that this carbon ion then reacts further with the alkylating agent, like maybe a primary alkyl halide, and then forms the derivative, the alkyl derivative of the dithiene, and then with further reduction, it will form the respective aldehyde. So the alkylation of the dithiene anion by a primary alkyl halide, or which we also call as a tosylate, it gives a thioacetal that can be hydrolyzed into the aldehyde. So what happens is that this thioacetal, it then undergoes hydrolysis. So it gives hydrolysis product as aldehyde using acidic solution of mercuric chloride. Then similarly, ketones can also be formed when both the hydrogen atoms are removed or replaced by the alkyl group. So in case of thioacetal, it will be thioketal. Then the third one is from nitrile. Nitrile means cyanide, and the most common name reaction is Stephen's reduction. So what happens is that the alkyl cyanide is reduced in presence of stannous chloride, SnCl2, and the product is first an intermediate aldimine, and then aldimine hydrochloride salt, and then which further hydrolyzes. So you can see if you do the hydrolysis of around the double bond CH3CHO, and then H2 will go there. So it will form acetaldehyde. Now you can see the mechanism down at the bottom also. So among carbon and nitrogen, carbon is more electropositive, and then nitrogen is electronegative. So the H plus will go to the nitrogen atom and the chloride will go to the carbon atom, and then it will form this aminochloride. Then further HCl will add. So what will happen is that HCl will add, it will form a salt with this NH group, and it will form aldimine hydrochloride salt. This further hydrolyzes, or you can also say that this aminochloride also, this can also hydrolyze, and then the product is an aldehyde. Okay. Now the next one is from carboxylic acid. So what happens is that carboxylic acid is treated with alkyl or aryl lithium to form an addition compound. So the intermediate is an addition compound, which then further decomposes to form a ketone. So how it is done, you see the mechanism. So first acetone reacts with methyl lithium, for example, with the removal of an alkyl group or a methane group, and then there is an addition product which is formed. Further on hydrolysis, what happens is that both the Li groups are removed. So LiOH, LiOH get removed, and then 2 OH groups are introduced. But we know that 2 OH groups attached to the same carbon atom, it is highly unstable. So one HOH or H2O molecule will get removed, and the product is a, here in case of this compound, it is a, in case of acetone, it will give further another this ketone. So, sorry, it's not acetone, it is actually carboxylic acid. So it will give propanol. Now, if you see the general physical properties, so aldehydes and ketones, they are mostly colorless and they are mobile liquids. And when there are carbon atoms more than 11, such aldehydes and ketones are solids. And aldehydes have an unpleasant smell, and the higher members have a fruity smell, and the ketones have usually a pleasant smell, and their solubility rapidly falls with increase in the molecular weight. Why? Because of the increase in the hydrophobic chain. So with the increase in the number of the hydrophobic groups or the carbon atoms, there is decrease in the solubility. Now there will be certain reactions. Common reactions are like reduction, nucleophilic addition, condensation, hydride transfer, condensation reaction with ammonia derivatives, and phosphine oxidation, polymer addition. We'll take up each one of them. So first we see the nucleophilic addition. So what happens is that nucleophilic addition means what? Addition of a molecule to the carbonyl group with the initiation of a negative part. So the negative part of the adding molecule, like if we take HCN or CN minus, so it adds to the positive carbon of the carbonyl group, followed by the attachment of the positive part. So when the nucleophile, that means the negative part, first attacks the carbonyl compound, then the product is the reaction is called as nucleophilic addition. And this addition, then it is shown here. So if you see the geometry of the intermediate, the transition state, it is a trigonal configuration. And in the transition state, it starts acquiring from sp2 to sp3 hybridization. That is the double bond character is going in the transition state, but then it is resumed in the final product. So that is why now what happens is that because oxygen is able to acquire this negative charge, that is why nucleophilic reactions occur in carbonyl compounds. Now it is found that aldehydes are more reactive than acetone towards nucleophilic addition. Why? So there are two reasons for it. First is the steric factor and second is the electronic factor. So the steric factor means because the nucleophile is attacking maybe from the top or the bottom, so more the number of carbon atoms, more is the hindrance. So lesser the number of carbon atoms or the alkyl groups, lesser will be the hindrance. So in case of aldehyde, obviously there is a hydrogen atom instead of an alkyl group. That is why, because there is less steric hindrance, that is why it is more feasible for aldehydes to undergo nucleophilic addition. Then it comes to the let's see the electronic factors. So what happens is that the alkyl group, it exerts, we know that it exerts plus I effect, electron releasing inductive effect. So what it does is that it increases the negative charge density on the carbon atom, which then makes it difficult for the nucleophile to attach to the carbon atom. That is why the transition state in case of ketones is destabilized, and hence the reaction is not very feasible. So more the number of alkyl groups, more will the plus I effect on the carbon to which the nucleophile is going to attach. And since already it is electron rich, so it will repel the incoming nucleophile, which is also electron rich. That is why, because of these electronic factors, there will be less reactivity in case of ketones than aldehydes. Next one is benzoin condensation. It is a very important reaction. What we have to do here is that we have to condense two benzaldehyde groups. Okay, so benzene rings will remain as it is intact. Now CHO groups we have to rearrange such that one of the carbon atoms retains the carbonyl functional group and the other one gets a hydroxyl group. So this product is actually benzoin. And that is what is called as benzoin condensation, and the reaction is done in the presence of KCN base. And now let us see the mechanism. So it occurs in 3 steps. So the first step is the formation of a carbon ion. So what happens is that first KCN splits to form a CN minus, which then attacks the carbonyl group in the second step. So the second step is the attack of the carbon ion or the nucleophile on the second molecule, and then the third step is the loss of this CN minus. So in the mechanism downstairs, you can see at the bottom. So what happens is that a cyanide group is attacking the carbon of the CO bond. So oxygen will retain the minus charge of the CN group. And then what will happen is that there will be rearrangement. So this H plus will go with the O. And then there will be a carbon ion formed. And then this carbon ion which is formed, it will react with another benzaldehyde molecule. And the final product is what we get as benzoin. Next important reaction is novel reaction. So an aldehyde or a ketone on condensation with a compound having an active methylene group. So active methylene group is like alpha malonic ester if we see. So the formula is like this. So it has a methylene group, that means CH2 group. So when it reacts with an aldehyde, what happens is that you arrange them such that you can easily remove this H2O group. So the product, whatever you do in presence, this reaction occurs in presence of a base, and then whatever intermediate you get, you hydrolyze it. So when you hydrolyze it, what you have to do is that it gives an unsaturated compound, which is crotonic acid. So similarly, if we take malonic ester, if we say acetic ester, what will happen is that first it will form an intermediate compound, and then further in presence of H2O acidic conditions, what will happen is that it will rearrange itself, and then it will give an acid. Okay. Next part is aromatic aldehydes and ketones are less reactive than aliphatic aldehydes and ketones. So the reason is that the phenyl group, it has an electron withdrawing inductive effect. That means minus I effect. So what we can expect is that the transition state, it will get stabilized in the nucleophilic addition, but this is not actually so. So what happens is that aromatic aldehydes and ketones are less reactive. So we suppose that it should be more reactive. Why? Because of the minus I effect of the ring, it should be resonance stabilized, so that should be more reactive. But in reality, this doesn't happen. Why? Because these aromatic aldehydes and ketones, they get stabilized due to resonance. And because of this resonance, what happens is that a positive charge is created on the ring instead of the carbonyl group. That decreases the chances of the nucleophilic attack. And then also because this phenyl group, it is a bulky group. So it will also cause steric hindrance. That is why they show less tendency for nucleophilic reactions. So we conclude that the presence of alkyl group decreases the reactivity of the aldehydes and ketones towards nucleophilic addition, while the presence of the phenyl group further decreases the reactivity. So greater the number of such groups present or bigger the size of the group, smaller will be the reactivity. So if you get a question like this, you're given like 5 compounds as given in the bottom, and you're asked to see which one is more reactive. So you just have to see the number of alkyl groups. More the number of alkyl groups, more will be the steric hindrance. I think the fourth option is incorrect. Now let us see the mechanism. It's the same. Just a minute. So that's all for this lecture today, students. The next part of this lecture we will take up in the next lecture. Thank you.